Hello everyone, welcome to this video. My name is Emerson Ahrari, I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate vegetation index using Sentinel-1 radar data in the Google Earth Engine platform. This is a useful tutorial for everybody who wants to study vegetation cover using radar or Sentinel-1 data. So, I'm using this reference in this tutorial, comparing Sentinel-1 and 2 data indices for agricultural land use monitoring. This is a paper already published in the MDPI journal, and now I'm going to show you the target index we want to calculate using Sentinel data. Here, as you can see, there is an equation. Equation number 1 refers to a full polarization data that could be used for vegetation cover detection with a good accuracy. But unfortunately, full polarized data is not available in Sentinel-1. That's why we have to use dual polarized data, such as VH and VV. That's why I'm going to use the alternative equation, the equation number 3 for the Sentinel-1 data. Because as you know, the HV and also the HH bands not available in the Sentinel data. Only VV and VH is available. That's why we have to use for equation number 3 to calculate vegetation cover situation. And as you can see, the equation should be done based on the sigma naught values. As you may know, in the Google Earth Engine, Sentinel-1 data already published in decibel formats, but we have to convert them before equation. So let's go back to the Google Earth Engine platform. In the first step, you must select your study area. The study area must be a farmland or something like that. So let me to select a region. For example, I'm gonna select the farmlands in the southwest of Iran. As you can see here, turn the view to the satellite, and now here you can see the farmlands. Not necessarily actually use the same study area. You can pick your own study area, and also depends on your target of interest. And also this tutorial can be used for all around the world, not limited to a specific location in the world, because Sentinel-1 is a public data and you can use it for all around the world. But the only thing matter is you must pick a farmland or an area covered by the vegetation covers. So now I'm gonna select the part of farmlands available here. Using drawing tools, you can see I can draw a rectangle using drawing tools available here, just like that. Next, to have a focus on the study area, try to use map.center object to have focus on your study area as a geometry. In the next step, a new variable as Sentinel-1 created. Go to search places on dataset and try to let's find the Sentinel-1 collection snippet here. Sentinel-1, as you can see, the collection snippet is available here, and click on import. Then you have it as a new variable in your code already named as an image collection. Now assign the image collection to the Sentinel-1. If you want to get understanding about Sentinel-1 data characteristic, just click on the data link here, and here you can see a full description about the data. And as you can see, the bands combination and also the information. As you can see here, the data is available since October 2014. And if you go to the bands, you will see the bands are available in different polarization. The polarization refers to the direction of electromagnetic radiation. HH means horizontal send and horizontal receive. HV, horizontal send and vertical receive. VV, vertical send and vertical receive. And VH stands for vertical send and horizontal receive. The direction of radiation in the microwave region is very important and may have impact on the quality of information we will receive. As you can see, the data available in decibel format, but we have to convert them to the sigma naught parameters. And the spatial resolution is about 10 meter, as you can see here. So let's close the band table and try to call Sentinel-1 data using particular filters available for this kind of data. The first, let's get started with filter date and filter bound. Filter date actually limit our data to the specific period of time or a particular time span. For example, I'm gonna call the data for 2023, the start date 2023 and the end date 2024. Then bound your data to the region of interest already drawn. Let's get a print to see how many Sentinel-1 data is available for this region. As you can see, we have focused on the study area because of the center object already defined. And here we have a variable included Sentinel-1 images. Around 87 Sentinel-1 data called here. If you go to the feature, you can see the data or feature characteristic. Each feature included couple of bands such as VV stands for vertical and VH vertical horizontal. So, and another one is the angle. For this tutorial, we don't want to use the angle band. So in the next steps, I will show you how to select the target bands. But here we have a metadata included different information about the product we are working. For example, one of them is a system time start, explaining the period of explaining the acquisition date with millisecond format. This is a typical format Google Earth Engine uses for time series data analysis. But another property that is very important for radar data is about, let's see, orbit, orbit properties past defines if whether this data is ascending or descending. The ascending and descending refers to a kind of orbit path that is important to filter the data based on, because the geometry of the data and geometry of the imagery is different in the ascending and descending format. So let's start to define the necessary filters for Sentinel-1 data. Some of the filters are necessary. We want to filter our data, actually the Sentinel-1 data, based on some particular properties that should be considered before further analysis. One of them is instrument mode. For example, here, make a new filter, Earth Engine.filter.equal. So I'm gonna use those data in which instrument mode equals to interferometric widths. Equal here, instrument mode equals to IW, interferometric widths. And another parameter is about, let's see here, there are different parameters. I'm looking for another one that is important, but I don't remember its name, just a moment. So yeah, the next one is transmitter receiver polarization. We want to use and we want to call those images in which transmitter receiver polarization including VV and VH, just like that. So now let's make another filter. It is better to call this filter before instrument mode filter. So Earth Engine.filter that least contains equals to. So here, as you can see, the property name is transmitter receiver polarization. Just copy and paste it here, just like that. And the next parameter and also the next one is the name. the VV or VH. As I mentioned earlier, most of Sentinel-1 data, or almost all of them, are available in VV and VH polarization. So that's why we need both of them, VV and VH. You can define two kinds of filters to have VV and VH polarization together. So let's run a code again, and still you can see we have 87 elements, meaning that all of the data already introduced here, all of them included VV and VH and IW as instrument mode. So the next thing is about the orbit properties passed, the kind of orbit the data must be actually filtered based on. If you want to see how many orbit properties pass we have here, it's very simple here. Just dot aggregate array allow us to see how many orbit properties pass as a unique variable. Using dot distinct, you can see how many unique orbit properties pass do we have here. So ascending and descending mode. So let's try to see which one of them has more frequency in our study area. Let's start with ascending first. So now a new filter created, Earth engine filter equal. This is an equal filter in which orbit properties passed must be equals to ascending mode. This is the ascending mode and descending mode. Let's get a print to see how Sentinel-1 works. Print Sentinel-1. If you run a code, you can see 61 out of 87 or 86 actually stands for ascending mode. And also this is a good frequency. Most of the data we have for this area prepared in the ascending mode. So in the next step, we want to actually select the target band that was VV and VH polarization. Let's select the target band VV and VH. Get rid of the angle band. The angle is also the incident angle band, also very important for radar data analysis, but not works in this tutorial. As you can see now, we have VV and VH with the existing properties, and all of them available actually with instrument mode as IW, and also VV and VH polarization in ascending mode here. If you check that orbit properties pass, you will see the mode is ascending. The imagery mode is based on the orbit mode is based on the ascending mode. So the Sentinel-1 image created completely. So in the next step, I'm gonna show you how to use these two bands, VV and VH, to calculate the target index. Here you can see the target index, how we can do calculation. It is very important. So in the first step, you need a new variable here. For example, a new variable, the index name is RVI. As you can see, this is RVI, stands for Radar Vegetation Index, RVI. This is our target index. This index also very useful for those of months and region that most of the time overcasted, meaning that's covered by the cloud cover. So in that case, we have to use the radar data, and Sentinel-1 is a good option still, at least for now, to calculate the vegetation cover situation without a cloud impact. Although the optical data such as NDVI index works much really better than RVI, but for the high latitude region and for the region covered by the cloud cover, it is essential to use the radar data to have access to enough accurate data, because the optical satellite data always suffering from the cloud cover, and cloud cover is a kind of noise enable you to get accurate information using optical indices such as NDVI. So the RVI equals to get Sentinel-1 data first and make a loop structure using dot map. Each input in the actually loop structure or each image inserted into the loop structure and called as img. You can pick any other name, not necessarily img. So you can choose any other name. It is an argument and it's totally up to you. So make a new variable here, and as index equals to, from using the input actually images, the input img included vv and vh. Just we need to know how to write this equation in the Earth engine. So now call the existing data using the img here, and then expression is a function allows you to write an expression to write your equation easily. So make a quotation marks here and make two parentheses for denominator and numerator. So the numerator, the 4 multiplied to vh, 4 multiplied to vh band, and also in the denominator we have an addition between vh and vv, vh plus vv, just like that. So vv and vh here are unknown, and we must define a known variable instead of unknown arguments here. So make a curved bracket inside, define your unknowns here. The first is the vv. From input image select the vv band, but the vv band is like that. It should be in capital format. So, and the vh, the next unknown, equals to, from input img select vh, just like that. Rename the output as a RVI. This is actually the radar vegetation index. The function and loop structure should return a result. The final result here is the index. Index returned by the function. Return index, just like that, with the properties of input images. There are a lot of properties here. You can see several of them, but none of them will be used in the next step. Only but a few one. For example, here the system time start is the main one for the time series analysis that is necessary. So this is the system time start, and here we can filter the properties using a bracket here. From input properties already named as a img, so here I'm gonna have the system time start and system time end, explaining the period of time or time span in which data acquisition is done. System time start and system time end. These two properties are essential for time series analysis in the Google Earth Engine platform. So let's get a print from RVI here. Print RVI and click on save. Again, 61 elements returned, but this time if you go to the data properties, you will find the RVI already calculated for this area. So, and now as you can see, here we have the system time start and system time end as the target properties only remained. So in the next step, I'm gonna do a visualization for the region of interest to see that if we can actually highlight or see the vegetation cover or not for the region of interest. Get rid of the geometry inputs by click off, and then use the map.add layer for the visualization. The RVI, so all indices already stored in the RVI. I'm gonna get an average image to show how the quality of output is. So the mean clipped based on the region of interest, based on the geometry here, and also here it is a blank bracket for the visualization properties, because the visualization or defining a kind of palette is not our target in this tutorial. Just I'm gonna show you a grayscale image that highlights the vegetation cover. So the layer name is RVI index and use the false at the end. Let's run a code again. Go to the layers, RVI is available. Click it on, and after a few moments you have an image with no enough information. To get a better contrast, go to the layer setting and increase the contrast based on the 90% of values available for this region of interest. The quality of output is not good because the output is actually created based on decibel format. Before going through the index, it is important to convert the decibel data into a sigma naught equation. So now define a sigma value variable before index. And also to calculate the sigma naught, first make an image structure included only 10 value, only value number 10. So that is squared to all band divided to number 10. This is the equation. Help us to convert the decibel format into sigma naught. So the sigma naught image is available here and replaced by the img replaced by sigma naught here. Let's save the code again and run it again. After a few moments, you will see the RVI index is available for this region, and this time you can see the vegetation cover highlighted for your region of interest. Even you can increase the contrast using 90% of values in the histogram here, or you can increase more and more to see the vegetation cover easier and better. As you can see here, we have a grayscale image in which the brighter area shows actually higher vegetation cover, and also the darker area stands for lower vegetation cover. Although this is not accurate as same as NDVI or other optical indices, but for cloudy time and also for a high latitude region, it could be very beneficial things. And remember that the RVI radar vegetation index sometimes actually included some noises because of the moisture content or physical properties of vegetation cover. So that's why you may see some misunderstanding values for the vegetation covers, and now you can see it has very high quality, but still can be a reliable actually alternative for the NDVI and other optical indices, at least for the high latitude region, in case you want to monitor actually the crop growth situation for your region of interest. Now in the next step, I'm gonna actually show you how to monitor the variation of vegetation cover from one field to another field. Let's make a new geometry here, and using the polygon, I'm gonna select a part of the field and see how vegetation cover, how actually growing value changes during the growing season. For example, I'm selecting this field here. Hopefully in this area we have big fields, and also clearly you can select a region and see the variations without any noises. When you have bigger fields, actually definitely you can have higher accuracy in the output. And remember that the output resolution is around 10 meter. That is very awesome for agricultural studies. Let's run a code, but I forgot to make a chart to show the RVI variation for this region of interest. Let's get a print here using user interface chart image.series here. Now instead of image collection, I'm gonna have the RVI. The region of interest is the second geometry created for the selected field, And for the whole of the field, the selected area with green color, I'm gonna get an average RVI during the growing season. Earth engine.reducer.min help us to calculate it, and also the scale is 10 meter because the spatial resolution is 10 meter, and use the system time start as a actually X property here. After a few moments, you will have a new chart that shows how vegetation cover changes during the growing season. Higher values, higher growing value, lower values, lower growing value. So let's increase the time span from 2020 to 2024 to see a growing season pattern in this area. So a new chart is generating here, and now clearly you can see the growing season variation when vegetation cover reached to the peak and then harvested. RVI decreased, and also it follows like that from 1 year to another year. So now you can compare it with the original data we already have in the Sentinel-1. So just let's make another print here, just like that, print RVI, but this time instead of RVI I'm gonna have the VV and VH bands. That's why instead of RVI the Sentinel-1 data called to see how actually backscatter value, the original backscatter value changes in this region of interest. So let's save your code and run it again. In the right panel you will have a new chart. In addition to the previous one, you will have a new chart that shows just meaningless backscatter variations that not gonna help you for actually assessing the situation or assessing the vegetation cover situation during the growing season. But hopefully, thanks to the index, we combined information already available in VH and VV, and now we have a vegetation index that help us to get more accurate information for the region of interest. So but still there is one problem here. In the RVI image, you will see if you have experience with the Sentinel-1 or radar data, definitely you know about the salt and pepper effect on the radar images. As you can see, we have some salt and pepper noises in the radar images that you can see as bright dots on the image. And it is important, if you want to get rid of these dots, it is very simple, and also you can use the low pass filters to make output image make a smooth output. If you want to make a smooth output, it is important to use the low pass filter. Otherwise, you can use these kind of images for the further analysis. But I will try to show you in the next video on my YouTube channel to see how to solve the speckle impact on the radar images. But before going through the speckle impact, let me to show you the different images we already have for the period of time. Let me to reduce the period of time to only 1 year, or no, we can actually filter them in a new map.add layer. So let's make a new add layer, but this time I'm gonna filter the data only for 1 year. For example, 2023, the start date 2023, and the end date 2024, just like that. And I'm gonna have all the images in a stack layer using those two bands that is clipped based on the region of interest. This is RVI for 2023. Let's save the code and run it again. So now you can see the actually speckle impact much easier and better. As you can see, this is salt and pepper impact in the Sentinel data. If you select only one image here, you can see the impact of a speckle actually on the output much easier and also clearer. Actually, this is an inherent characteristic in the radar images, and it is important to solve this issue in the satellite, in the Sentinel-1 data. For example, if you go from one date to another date, definitely you can see more spectral impact. In the first image, actually, we got an average for the whole period of time. In that case, the spectral impact actually solved because of the averaging technique. But if you are working with a single image, definitely you will face with such kind of characteristic. There are some time series analysis that allows us to get rid of the speckles in the Google Earth engine. But here, the simplest way, if I'm gonna share a simple method with you, it is about the low pass filters, because time series analysis might be a little difficult for the users in this tutorial. I will try to make another video about how to smooth the spectral impact in the radar images. But the simplest method here is actually a smoothing technique using low pass filters. Get the index first and then try to define a low pass filter using the focal median. For example, the focal median is a low pass filter that helps us to smooth the output. Set a radius first. The radius actually resampled our data to the number we set here. For example, the 30 is the target number for the resampling process, and the kernel type should be square format because pixels structured in the square shape. I prefer to use the square one here, and the units could be meters. So actually I'm smoothing data using 30 meter based on 30 meter resolution, and I skip the rest of the parameters. And remember to replace the index by smooth to see how a smoothness actually, or a smoothing process, helps you to get a better result here. So now let's select a target date, for example the first one selected here, and increase the contrast and click on apply here. As you can see here, the speckle the image actually highly improved compared to the previous version. There are the other, as I mentioned earlier, there are better methods in the time series analysis, but I will prefer to show you that method in another tutorial because it is beyond the information we want to actually present it in this tutorial. So, or another date, if you select the another date and increase the stretch here and increase the contrast using a stretching technique here, you can see sometimes the actually, yeah, now it's better. Sometimes we will have some problems for visualization process. The brighter region shows higher vegetation cover, and also the darker area lower vegetation covers. So, and it is important to know that the radar data are highly sensitive to the vegetation physical structure. For example, if we have more density, then we will have higher backscatter value. If we have, for example, taller vegetation, we will have a higher backscatter values. And even sometimes, and also it is important to, it is highly important that the radar data is also highly sensitive to the moisture content, and sometimes higher backscatter value could result in, actually resulted from high moisture in the vegetation contents. So these are considerations that you must actually consider for your study, and also try to read the articles to get more understanding about RVI index implementation. So now here I'm gonna show you how to get export from the RVI index that is already created here. Definitely you know how to get export from the charts. Here you can go to a new page and download as a CSV file, allows you to have Excel format for the output. But here, if you want to get export from the raster layers, it is very important to use Earth and user interface so export that image to drive, just like that. Export that image to drive created here, and now the first image, the image we want to get export is, for example, RVI images for period of time that is already clipped here. And the next one is this description. Description is an argument, refers to the output name. This is the RVI. Region of interest equals to the geometry, the first geometry, and a scale for the output now is 30 meter because we used a smoothing process and low pass filtering that reduced the spatial resolution to 30 meter. Definitely, literally, I'm recommending to see the next video on my YouTube channel that will be uploaded in a few days, and then you can see about and you can understand about more complex and also the advanced method for a smoothing process that helps you to increase the accuracy for your tutorial, for your purpose here. So this is the scale 30 meter, and the region of interest already defined here. The coordinate system is WGS84, but instead of WGS84 we have a code EPSG4326. And you can also define a folder for the output. For example, I make a simple folder as a test to have an output there. And the next parameter is about the maximum pixels. When you are working with the mid resolution satellite data in 10 meter or 30 meter, it is important to define the maximum pixels, the maximum pixels you can have for each image type when you are doing when you are working on export process. So the maximum pixels equals to 1E13. This is the maximum number. And now let's run your code. In the right, if you switch to the task, after a few moments you will have RVI that is ready to save. Just click on run, and after a few moments the tabs color turn to the blue, just like the before examples, and then you can pick it up from your Google Drive and open it up in your own geospatial software. I hope you like this tutorial, and I highly asking you to share this tutorial with other users in remote sensing community. The code link is also available below the video on my YouTube channel. You can compare yours with mine to solve your questions. Feel free to reach me out on my YouTube channel and put your comments there. I will try to answer your questions as soon as possible. Thank you for your attention.